Hey, what's up, world? And Happy New Year! 2021 has already started, and this today is the 3rd of January. Alright, so I'm gonna upload this continuation of what we started to do with connected particles. As you remember, we went through theoretical basis, how the formula works here, and I explained actually the idea of this model where you can apply this connected particles model. And also we have AP and challenging level problems for ALevel. That's going to be the right time in order to try your best in solving those kind of problems. So I think it's going to be useful and much more appropriate to exam styles questions. So that's why I think it's right to do. Okay, so let's have a look. So problem 1 definitely can be solved using the idea of connected particles. Let's have a look at the conditions. So what you have here. So you have a locomotive, definitely a greater mass than a freight car, which is in front of it. And they connected with, kind of a shunt. Let's have a look. And let's set up this shunt is, basically, a connecting thread or rod. As you can see here, which always stays horizontal position means it's parallel to the railway track, where you can put the railway track over here like this. And this is going to be a loco. I just denote that the mass of the loco is great, let's say big M right here, and a small m is the mass of the freight car. In this case, this type of the car hopper, that's used for just carrying the grains and transferring grains of this sort of substances. Alright, so that's why I just put small m and big M. Okay, so what we're gonna do, they definitely connected with this road, with this shunt, which can be in this question has a negligible mass. That means we don't take into account extensibility of this thread or shunt itself, and actually we're going to use a negligible mass. So that's why this allows us to apply the model of connected particles for two objects, the locomotive with a greater mass m and with a small mass m, the hopper itself. Okay, so because locomotive pushed the hopper which is in front of it, and you see that permanent driving force of 500 kilonewtons applied. That means the engine of the locomotive produced this force, so that means everything accelerated with the same uniform acceleration, which is constant, 2 meters per second squared. Okay, that's acceleration. What we're gonna do, we need to set up the force that acts on each separate object, or we can consider the whole system of two bodies as the whole one object, and we can, maybe it will simplify our observation and our solution for this problem. So that's why I'll show you two ways how if you separate them and if you consider it as the whole one. So first of all, let's separate and let's consider each object in the system as the separate object, and let's have a look at the influence of the force. All right, so in other words, we are going to draw up the force body diagram or free body diagram. All right, so that's why we input x-axis as the positive direction of the motion, where you have acceleration towards the positive direction of this axis. And for hopper, which is here, a car, there is how many force acts on it. So first of all, from a shunt, due to the locomotive push that, we have a force which is here, and we set up this force as T. Okay, it's to the right, definitely, because locomotive push that. All right, so what's next? We do have the horizontal resistance of motion for the hopper, 5 kilonewtons. It's right here, it's against the motion, and we can set up F resistance 1, which is equal to 5 kilonewtons. Okay, So we do have pushing force, which is T. So you know, if you just apply this and consider shunt itself, it's going to be a tension actually, or force of compression itself. But for the hopper, that's the force that acts from the side of locomotives through the shunt. So that's why you don't care about the left-hand side, but you imagine as if locomotive just pushed that. So it's kind of pushing force. Okay, so we actually finished with that one, and let's consider locomotive itself. We do have a driving force that's 500 kilonewtons. So let's set up this force right here. That's going to be driving force Fd, which is 500 kilonewtons. Okay, it's right here. It's to the right. So we do have some resistance to motion that acts on the locomotive. Is now dependent on speed, and we input Fr1. Now it's already done. Fr2 for the locomotive itself. This is resistant force against the motion. And what else? We do have the same force, which we mark as T, but the opposite side. It opposes motion because that's from the side of the hopper, as if it's some kind of resistance, okay, to the motion. That's enough, and let's set up the second Newton's law. Now we apply the second Newton's law and complete the equation. So we have for locomotive, which force acts on it. So first of all, it's going to be a driving force, F driving. Then we do have minus Fr2, resistance to the motion, and minus T is going to be equal to m times acceleration. I'm not going to plug the values until I just definitely know what to do, and I just want to figure out the whole formula first of all. For the small mass, for the hopper itself, we do have two kind of force, that tension force that pushes and resistant force R1, okay, that against the motion, and is going to be equal to small m a times a. So as you can see, the right side is the resultant force, which is expressed through acceleration times mass for each object, and the left side represented by, by each component of force, each component of the resultant force, which is breakdown by the forces that we draw up here, okay. How to solve? We don't care about the tension in this question, so that's why we need to kill this variable and we solve as the system of equation. Okay, I'll mark as the system of equation, and what I'm going to do, I'm going to just add, because I see t and negative t will be cancelled in this case. So in that case, we need to find resistance from there, so that's why first I'll add them up, and I'll get Fr2 minus Fr1, and because I've added them, I add in the right sides, but I'll factorize acceleration from there. And what I have right now, I have an equation where I just set up with a green or maybe with a blue one, all variables that I know. I know the driving force, definitely. I know Fr1, that's against the motion, the resistance against the motion for the hopper. I know that, I know total mass, so I can figure out Fr2, which is basically the target variable in our equation. So that's why I'm just going to right now, I'll express Fr2, and from here I just transfer to the right side, and I'll have F driving force minus Fr1 and minus a times m plus vgam. So that's the final, the final result for Fr2, from where I can calculate. But for purpose of comparison, I'll just, to put it in frame in order to see what we have here. All right, so let's do right now, for the reason of to stay consistent, to be consistent, I'll just try to diminish this and maybe just go a little bit here, because we've got that, and now the left side is our force and I need to calculate. So what I have, I have 500 kilonewtons, so I'll use the units for the force in kilonewtons. I'll write 500 minus FR1, which in our case is 5. Just take away 5 from here, and I also need to take away acceleration, which is 2 meters per second, to multiplying by the total mass. The total mass is going to be 127. So 127. So that's why finally FR2 in kilonewtons, I'll get 495. And minus 2 times 127. Okay, because I do have tons, actually. You understand that actually this part is going to be in kilonewtons because tons is simply 10 to the power 3 kgs, right? So if I use that, actually this part is going to be in kilonewtons. So that's why I'm okay with that. I'm not going to apply this power, cubic power of 10. So I'll just simply multiply them. And I'll get 254. 254, okay? And if I take it away, I'll just simply get 1, 4, and 2. And I'll get 241 kilonewtons, the resistant force that acts on the locomotive, all right? So I hope you got it, but for comparison, I'll show you just a bit different approach, as if I consider the whole object as the single one, you know. So that's why I just move here. I have the same actually problem here, and I just combine them. By combining them into a single object, what's the purpose for that? I'll just simply exclude all internal interaction of two bodies within the system. So that means right now I have a single object that basically include the locomotive and the hopper itself, and I'll consider only the force that acts on each part of the body, but as if I applied to the whole object. That idea will simplify our solution in that case. So what do I have? I have, of course, F resistance 1 that acts on the hopper, which is equal to 5 kilonewtons, and I do have FR2 that is unknown that acts additionally onto locomotive. That's our target one. Okay, what I do have the driving force that acts to the right. And that's it. You see, there's much more, simplified version of what we've done before. So that's the easiest way. And if you don't care about any internal force that acts within the system, just you can combine them into the whole system, and basically you simplify the steps that we've done here. All right, so let's do that, and let's complete for the object m plus m, the second Newton's law. So I multiply by a, because the whole object has acceleration a to the right, and this is the positive x direction. So I'll get driving force minus FR1 and minus FR2, from where I can express FR2 with no problem. It's going to be F driving force minus FR1 and minus 8 times m plus m. This is going to be much easier, and it took just 2 minutes to go through, all right? After you've got complete understanding of what's happening, all right? So, okay, we've done with that, but unfortunately, using this approach, we cannot find the answer to question B. So that's why we just come back and we use equations that we've accomplished before, because they're much more simple, and they're much more appropriate to the question B. Okay, so we care about the compression force in the shunt, but hold on, like you might ask the question, so what's the compression force? Let's consider shunt. So if you start applying the approach that you consider shunt and thinking about, okay, you apply the third Newton's law and say, okay, instead of two forces that act on that way, on to the right and to the left, you apply the concept of the third Newton's law, that those forces are the same but acts in the opposite way. That's exactly what you have for the shunt. And you'll be right. But because the mass of this shunt is negligibly small, and if you try to complete the equation, mass of the shunt times acceleration, and you apply this approach, you just simply have the difference, you'll get 0. Why? Because actually, you use that idea, and in reality, the force will be different. For example, this force is going to be T1, this force is going to be T2. And what you'll have the difference, because the shunt is going to the right. You'll have T2 minus T1. And in general case, it's not equal to 0, but you assume that mass of the shunt is 0. So hence you can think that T1 is equal to T2. Okay, so the assumption that leads to the outcome, the equality of the tension force that acts on their shunt, or compression force. But how would you do that? Finally, you still didn't get the solution for that. Okay, no problem. Let's remember how we consider a spring. Let's have a look here. So you have the spring suspended, and you have a load which, due to the gravity, acts on this spring and basically stretch it. You understand that the single force that acts on this object is the force of elasticity. According to Hooke's law, it's proportional to the extension, right? So it's proportional to extension delta x, due to the fact that this load actually is heavy and it pulls the spring down. But you ask about it again. Let's compare with what we have for the shunt right here and what we have for the spring right here. What's the compression force? In our case, we do understand that this elastic force is actually the force that applied to the spring, and that's why it's extended due to it. We understand that also if we consider two forces that acts on the spring itself, there are two types of force. Again, elastic force that acts, the elastic force that acts from the load downward, and the reaction force that withhold the top end of the spring. And there again, they're equal because of the spring of the mass is negligible. But the force that acts on the spring basically becomes the stretching force. In case if it's compressed, like in our case, it's going to be the force of compression, but this is the one force, the single force. So that's why if you see this analogy, you definitely can answer to the question B. So the tension force becomes the compression force in our case for the shunt. So you can choose any T you like. For example, let's take here from the second equation for the small mass of the hopper and express T. That becomes the compression force. Compression force. And we can straight calculate that. It's going to be FR1 plus, so 45 tons, right? Which in our case is MA. So we just can add to 5 kilonewtons. We can add M times A, which becomes 45 times 2, okay? This result also will give us kilonewtons, okay? So we'll get how much? 45 times 2 is 95 newtons. Kilonewtons that acts on the shunt, due to the fact that it's between locomotive and the car, and due to the fact that the locomotive actually acts on the car and pushed it. So finally, we've got the result for the compression force, which in our case becomes 95 newtons. And that's going to be the answer to question B, okay? So that's why I just move here and say that finally the compression force, TC, becomes basically 95 kilonewtons. Okay, so I hope you got it. And actually, I would like to set up the result. 241 kilonewtons. FR2, 241 kilonewtons. Okay, so I think that's the complete explanation for all all details that might be confusing for understanding and for proper comprehension, I thought that it's going to be much more than enough, and you got it. And you just simply apply this concept to whatever problem you have. In the next video, you'll see maybe more interesting problems where there will be more than two bodies, two objects connected to each other, and that's going to be interesting. And also through the connected over the pulley, when the thread is passed over the pulley, it's much more interesting questions. All right, hope you got it. Consider subscription to my channel, and don't forget to like this video and share with others who still struggle with mechanics. See you in the next episode. Peace out.